Hello students, welcome to my YouTube channel. In this video lecture, I am going to answer the last remaining questions from sample paper number 4, RK Bali 4th edition navigation book. So let's begin with question number 91. Aircraft DME receiver does not lock onto its own transmissions reflected from the ground because why? So now, aircraft DME distance measuring equipment is based on secondary radar. Okay, it's based on secondary radar. Secondary radar uses two different frequencies for transmission and reception. Okay, so one for transmission, another for reception. Primary radar uses one frequency throughout its operation. The frequency at which it will transmit the radio wave will be the same frequency at which it will receive the reflected wave, the echo. Okay, so let's say this is your ground surface. There is a DME station here. Okay, there is a DME station here. Aircraft is in the atmosphere. Now, in case of distance measuring equipment, your aircraft becomes the interrogator, and the DME station on the ground will become the transponder. So, I am writing it here, interrogator, and the DME ground station becomes the transponder. Now, this aircraft will transmit a radio wave in the correction radio pulses in the direction of this DME station, okay, at an interrogation frequency of 1090 megahertz. The DME ground station will wait for 50 microseconds. 50 microseconds. After a delay of 50 microseconds, it will retransmit this radio pulses towards aircraft, okay, towards this aircraft at transponding frequency 1000 1030 megahertz. Now, always remember the transponding frequency, or the frequency at which this DME station will send back the radio pulses towards aircraft. That transponding frequency will be interrogation frequency plus minus 63 megahertz, plus minus 63 megahertz. Okay, so this is how the interrogator in your aircraft is able to determine whether the reflected signal, or whether the signal that it is receiving belongs to the DME station or belongs to any ground reflection. Now, if there is any signal coming from a ground, a reflection from the ground, that signal will have the same frequency as the transmitted frequency, because it's merely a reflection. But a signal or pulses coming from the DME station will be at a separate frequency. Okay, frequency separate from the transmitted frequency or interrogation frequency. So that is how your aircraft is able to distinguish between reply pulses coming from the station and just any other ground surface. So the correct answer here is they are not on the receiver frequency. DAB uses ultra high frequency band, that is right, but that is not the correct answer to this question. Statement is right, but it's not the answer. Now the pulse recurrence rates are varied. This statement is right, but this is not the answer to this question. Now, there is another question that can get asked when it comes to DME. The first question is this one. How does a DME receiver in your aircraft distinguishes reply pulses coming from a DME station, reply pulses coming from the ground reflection? The second question that they can ask is, how is the DME receiver in your aircraft able to distinguish between reply pulses made for itself, intended for itself, and reply pulses intended for some other aircraft? Right? So it is able to distinguish between its own reply pulses and replies meant for some other aircraft by changing or by varying the pulse recurrence rates. So this will be the answer to that particular question. How is it able to distinguish between different reply pulses meant for different aircraft? Question number 92. What will be the rate of descent when flying down a 12% glide slope at a speed of 350 knots? So when the question includes or when the question asks or has a mentioning of 12% glide slope or any glide slope in terms of percentage, what you will do is you will use this formula slope equals to tan theta multiplied by 100. Now the slope given to us is 12%. That is equal to tan theta divided by multiplied by 100. So tan theta will be 12 divided by 100, that is 0.12. So theta will be equal to tan inverse 0.12, which is equal to 6.8 degree, approximately 7 degree. So this is your glide slope. Now step number 2, rate of descent is equal to the speed of your aircraft multiplied by the slope divided by 60. Now ground speed is 350 knots. Multiply this knots into 101.3 to convert the units in feet per minute. Multiplied by slope of 7 degree divided by 60. So 350 into 101.3 into 7 divided by 60 is 4136 feet per minute. So select that option which is closest to this value. So 4136. So we have 4255, 4283, 4382. So, so the closest option here will be option A, 4255. Okay. If the pressure feed line to a barometric altimeter becomes detached from the back of the instrument will indicate what? Now, your barometric altimeter is a pressure altimeter or it's a pressure instrument, let's say. It's a pressure instrument. That means it requires some kind of atmospheric pressure for its functioning, and that pressure is static pressure. Static pressure is nothing but ambient pressure, the pressure surrounding us right now. So whatever static pressure is fed in the instrument, right? That static pressure will be the static pressure is fed as an input into the instrument, and that is converted into corresponding indication in terms of altitude, height, pressure altitude, depending on the altimeter setting that we put in the Boltzmann window. Now, if the pressure line or the static pressure line which brings static pressure from static ports into the instrument gets detached from the instrument, what will the altimeter indicate? So in that case, so remember, in that case, there are two answers in this case. So first answer is if you are flying a non-pressurized aircraft. If you are flying a non-pressurized aircraft, if you are flying a pressurized aircraft. Okay, a non-pressurized aircraft and pressurized aircraft. In case of non-pressurized aircraft, what will happen? That non-pressurized aircraft means cabin pressure, the pressure inside your plane is equal to the pressure outside your plane, right? So all small general aviation planes or planes that are restricted to small cruise altitudes which are around 10,000, 13,000 feet. So these planes will not necessarily have cabin pressurization. But all those large planes, fast planes which are meant for operation at higher altitudes, more than 15,000 feet, 20,000 feet, 25, 30,000, these planes will be pressurized. Because when we go to or travel to higher and higher altitudes, atmospheric pressure decreases. When atmospheric pressure decreases, your bodily functions will get impacted. Okay, so we require adequate atmospheric pressure for lungs to function, for hearts to beat, function, and for oxygen, for respiration, and all that. So we need pressurization. And since we do not have adequate atmospheric pressure at higher altitudes, we have made cabin pressurized. We have artificial solution to that problem. We seal our fuselage, we seal our cabin, okay, and we provide pressurization inside the cabin. So that is a pressurized aircraft. So we may be flying at very high altitudes, 30,000, 35,000 feet, but the environment or the atmosphere inside the cabin will be like as if we are flying at 8,000 feet, 10,000 feet. Okay. So atmospheric pressure at 40,000 feet will not be felt inside the aircraft. We will still live uh, under atmospheric pressure existing at 8,000 feet, 10,000 feet. So that is a pressurized aircraft. Now, if a static pressure line of a non-pressurized aircraft, okay, static pressure line of an altimeter in a non-pressurized aircraft gets detached. So in that case, the altimeter will show a zero indication because there is no static pressure input from outside in the instrument. So zero. In a pressurized aircraft, it will show cabin altitude. So in a pressurized aircraft, whatever pressure is in the aircraft, in your cabin, that pressure will enter the altimeter instrument from the back, and that pressure will be decoded, will be registered, and an vertical distance, altitude, height, whatever, corresponding to that pressure will be indicated to you. So basically, you will be shown cabin altitude. So the correct answer here will be if the pressure field line. So it will be read cabin altitude. So it's safer to select option Bravo, read cabin altitude. Okay, next. Question number 94. If temperature increases by 5 degrees Celsius during a constant Mach number descent, what will happen to calibrated airspeed? Now, you are descending. So let's say this is a particular atmospheric layer. So what happens when you descend down to lower and lower altitudes, atmospheric pressure increases. When you climb to higher and higher altitudes, atmospheric pressure increases. Now I have said this many times in many of my lectures that your calibrated airspeed is nothing but the speed shown by your airspeed indicator. Correct? Speed shown by the airspeed indicator. So airspeed indicator is nothing but your pressure instrument. It's nothing but your pressure instrument. And it requires dynamic pressure for operation. Dynamic pressure for its operation. This dynamic pressure will be registered in the instrument and indicated in terms of knots, that is indicated airspeed of line or calibrated airspeed of line. So whenever you're descending down an atmospheric layer, whenever you're descending down an atmospheric layer, what happens? You're descending down an atmospheric layer, atmospheric pressure increases, right? Atmospheric pressure increases. Now, when atmospheric pressure increases, the dynamic pressure registered by your aircraft instrument will also increase. When dynamic pressure increases, calibrated airspeed will automatically increase. Contrary to this, when you are climbing to higher and higher altitudes, atmospheric pressure decreases. Atmospheric pressure decreases. If atmospheric pressure decreases, automatically the pressure registered by your airspeed indicator, that is namely dynamic pressure, static pressure, all that will also decrease. As a result of which the indication given to you by the airspeed indicator will also start decreasing. You may be flying at a constant true airspeed, you may be flying at a safe airspeed, okay, but the speed indication given to you will start decreasing. That doesn't mean your actual flying speed is decreasing. It only goes on to say that or tell that the speed indication shown to you is decreasing. Okay, so when you come down, atmospheric pressure increases, as a result of which dynamic pressure registered will increase and calibrated airspeed will automatically increase. So option A. Now remember, your calibrated airspeed is only and only dependent on atmospheric pressure. It's not dependent on temperature. True airspeed is dependent on temperature. Local speed of sound is dependent on it. But calibrated airspeed is not dependent on temperature. Whether the temperature increases as you come down or temperature decreases you coming down doesn't matter. That is, it's only given here for confusion. Remember, calibrated airspeed, atmospheric pressure. Next, question 95. What does Mach number represent? Calibrated airspeed of aircraft as a fraction of local speed of sound. Local speed of sound as a fraction of calibrated airspeed of aircraft. Indicated airspeed as a fraction of local speed of sound. Now we all know that Mach number equals to true airspeed of your aircraft divided by local speed of sound. That means the true airspeed of your aircraft with respect to the local speed of sound. Mach number is true airspeed of your aircraft with respect to local speed of sound. So we are making a comparison between the true airspeed of aircraft and local speed of sound. Let's say we are flying at ISA mean sea level. Over there at ISA mean sea level, the local speed of sound, is equal to 661 knots. And at ISA mean sea level, if the true airspeed of your aircraft, the speed at which your aircraft is really flying, is let's say half of this, 330 knots approximately. So Mach number will be what? TAS divided by local speed of sound. TAS as a function of local speed of sound. So TAS is 330. Local speed of sound is 660. So it will be half, which is 0.5. That means half or 0.5. That means true airspeed of your aircraft is half of local speed of sound. So Mach number 0.5 or half means TAS is half of local speed of sound. If TAS of your aircraft is also 661 knots, that means the true airspeed of your aircraft is equal to the local speed of sound. So in that case, the Mach number will be equal to 1. That means you are flying at the speed of at local speed of sound. Okay, very fast. So therefore, Mach number is TAS as a represented as a with respect to local speed of sound, fraction of local speed of sound. Now here the options are CAS and IAS. I guess or I think this is a printing error. It should be TAS, not IAS. So pay attention to this question in your exam. It should be TAS as a fraction of local speed of sound. Airborne instrument equipped with a gyro, 2 degrees of freedom and horizontal spin axis is a DGI. Next. Airborne equipment equipped with gyro, 1 degree of freedom and horizontal spin axis is turn coordinator. So remember all the three gyroscopic instruments, the basic properties, number of gimbals, the axis, spin axis. Okay, so very scoring. In a standby compass, the magnetic system is immersed in a liquid, methyl alcohol. The purpose of this liquid is dampening. Dampening. Dampening what? Dampening any oscillations. When you dampen all the oscillations or vibrations of that magnetic assembly, you increase a periodicity. So correct option is option A. Increase sensitivity of the magnet and increase a periodicity. A periodicity means tendency to remain stable, not to swing from one end to the other end. That is a periodicity. So when compass is immersed in a liquid, it increases a periodicity or magnetic assembly is stable. Question 99. Departure between two positions at same latitude 60 north is 1800 miles. What is the longitude of your destination? So, Rumline distance is equal to d log in minutes into cos lat. So, 1800 nautical miles equals to d log in minutes multiplied by cos of 60. So, d log in minutes will be 1800 divided by cos 60 is 3600 minutes or 60 degrees. Now, your first position is in the eastern hemisphere and you are flying easterly direction. So, for all Rumline diagrams, Rumline sums, draw Earth like this, draw the Earth like this. North Pole, you are looking at the Earth from the top of the North Pole. Prime meridian 180, east and west anti-meridian 90 east, 90 west. Correct? So your initial position is 60 north, 160 east. So 160 east is, let's say, here. What is your final position? Now final position is to the east of 160 east. Easterly directions are anti-clockwise. Okay, are anti-clockwise. So your final destination can be between 160 east and 180 east in the eastern hemisphere, or it can be beyond 180 east west anti-meridian and in the totally in the new hemisphere, western hemisphere. D long here is 60 degree. 60 degree means now total D long between 180 anti-meridian and initial location is 180 minus 160, D long 20 degree. So our total D long is how much? Our total D long is 60 degree. Out of that 60 degree, 20 degree will be traveled in the eastern hemisphere up to this anti-meridian. So remaining D long will be 40 degree. So remaining 40 degree D long will be traveled in the western hemisphere. So like this. So the final location will be 180 minus 40, 160, 140 west. 140 west. Okay. So option Charlie is the correct option. So this concludes our lecture. I hope you have understood all the questions I've done in this video lecture. If you have any doubts, any comments, feedback, let me know in the comment box of this video lecture. Keep practicing these questions. I have solved all the questions from this particular sample paper. More practice, more confidence, more perfection, more excellence. Okay, and better time management also. So now that you have solved all the questions with me, you can solve this paper again. Set a timer of 2.5 hours, not 3 hours. Put a higher limit on yourself. Put a timer of set your timer to 2.5 hours and try solving this paper of sample paper 4 without looking for any answers, explanations. So it's just the paper in front of you, a couple of rough sheets and an OMR sheet. Okay, and uh, and try solving this paper on your own in 2.5 hours. Score at least 85 marks. Okay, I wish you all the best. Best of luck. I request you all to share this video lecture with your friends who are also preparing for various exams. Subscribe to this channel if you haven't yet, and hit the like button if you have liked this video lecture. Best of luck.